Sheikh Zahid, and I represent the time response in control system in a short description. The presentation is submitted to our Professor Dr. Fatria. What is time response? And system representation, we have transfer functions and also state space. We'll have a short description of it in next slides. Importance of evaluating transient response. Before we go to the chapter 5, that is closed loop modeling, we have to know the importance of evaluating transient functions. And also we'll have a brief explanation or description of the poles and zeros. What are the what is their importance? First of all, we'll have a discussion of two parameters, two important parameters, the poles and zeros. Every output, any output systems is a submission of the two response, forced response and natural response. We'll have later on see, but definition of the poles that is shown in a cross sign. It is actually the value that makes the transformation 0, or we can say the root of the denominator. Why? Because if you have in denominator anything 0, it means if you have in denominator, for example, sorry, the definition I told makes the transfer 0. No, makes the transfer function infinity. If we have in denominator, for example, here 0, here any value, suppose c, constant value, c divided by 0 equal infinity. We will have infinity. Next one, the definition of 0 is mathematically inverse of the poles. That means anything that makes the transfer function equal 0, or it is the root of the denominator. If we have something that makes the denominator 0, for example, it is suppose it's 0. If we have any value in denominator, it will become 0. This definition of 0 here. It is also shown as simply O, or that is take it Z. The importance of zeros and poles. How a poles, how a, for example, how system or how to predict when a system is under an input or a side input. This is the importance of the poles and zeros. How to predict or how to predict a behavior of a system when a sudden input comes to the systems. Here is an example of poles and zeros. Suppose this example, this one. Suppose this function. We will have mathematically using the Laplace and this transfer function, and also we will using the mathematics we will find a and b easily. If you take this part out, take this part out, and this part, and this part, multiply this one to this one, a to this one, we will have something here. Briefly, it is taken from O. Briefly, we will have something like this, the value of a like this. If we put when s is equal 0, it means our a value is 2.5. When s is equal -5, s is equal -5. Here is -5, for example, in numerator, sorry, in numerator, sorry, when we have this one, -5 to 2, -5 plus 2 is 3 over 5. -5 plus 2 is -3 over -5, minus 3 over 5. Have the value. We'll solve easily. Our time response actually of this transfer function is this one. This is the important. We call this one forced response. Sorry, it is written force, but it is forced response, and this is natural response. Why we have a natural here and an exponential. In natural response, we have an exponential. If you read, you can read the text and also get more information. Example: poles and zeros. Again, we will have a representation of this graphical or imaginary representation. Look at this. This take from book. We have a simple system like this. We have an input RS, that is input pole. Suppose this input pole RS. We will have GS. GS is the value of GS we have. Our zero system, or system 0, that makes that system 0 is plus 2. What we will have here, what we will have here, value. When we have here a value here, a value that makes this one 0, it is actually -2. Yes, -2. Yeah, -2. This -2. This -2. That is makes the transfer function 0. And our system pole that makes our transfer functions infinity is what? -5 here. It is -5 here. If you put -5 here, then the function will become infinity. This -5. This pole -5. Put -5 here. This is the output transfer function. This is the output. Time in terms of the output. This CS. This one. We will have output time response. How? Easily. This will become input step. Input steps usually shown as the forced response. And this one, natural response. Natural response. Okay. Hope it is clear. Go next one. In first order system. A first order system is actually a simple structure that responds to an input directly or straightforward. We have some parameters. Here is an example of the simple example. Suppose this one directly. We are k. It is not constant. It is a gain. Could be different, but a is constant. A is constant. Okay. The transient response. What is the transient response? We have two parameters in transient response: step response and also time constant. We will have to move also. The step response, how a system, for example, when an input comes, how a system gradually approaches to the steady state. The time constant, how it takes long, how it fast reaches to steady state. We will have description now for the time constant next slide. This graphical will short description and next slide. Inshallah, we will have it of this graph. Look at this time constant. time constraints, I told that it is uh, how quickly a system reaches to steady state, or the time to rise to 63% of this final value, or we can say to reach to 37% of its initial value, and that is this one, this one, this one, this one. This is the time constant. Okay. Uh, Next one we have something. There are two more transient response performance specifications. That is rise time. Rise time is actually, according to previous graph, it is the time to rise from 10% till to the 90% of the final values. If we take CT, it means it is between CT equal 0.1 and CT equal 0.9. We will have, if we solve, we will have, according to previous graph and previous example, previous transfer function, we will have the following solution. When CT is equal 0.9, our time or time rise will have this value, minus when CT, sorry, when CT is equal 0.1 value, 0.1, the value, we will find the time rise by this value. We find the difference between these 2 points, that is the result. That's all we call time rise. The second parameter is settling time. Actually, what's settling time? The time that the system remains at 2% of its final value. Remains within the 2% of its final value. We can show it by the TS, that is this one, time to reach 2% of its value. If we have, how we can find? If we have CT equal, we said 2%, yes? It means 0.02. If we have CT, then CT equal 0.02 minus 1 as 0.98. If we have this value in CT, put this value in CT, we will get the time, settling time is 4/A. That's okay. That's okay. Sorry. The next one. Second order system. Second order system is a little bit more complex system that shows different responses based on their parameters. We will have some parameters here, some responses here. That is overdamped. What is overdamped system, and also underdamped and critically damped. We will have a short description of each damps in the following. Actually, overdamped, the slow response. Overdamped means the slow response. or no isolations. We will have our transfer functions as this. At poles, real parts as 2. In poles, we have real parts as 2 sigma, sigma 1 and sigma 2. Okay. Natural response. In natural response, actually, we will have a exponential that is its time constant is the reciprocal of the what of the pole value, reciprocal of this. We have an attempt oscillates before settling down. It means the system oscillates until it reaches the settling. Our transfer function will be here as we'll have underdamped. In underdamped, we have two complex at what? At sigma. One is at sigma, the other is at omega d. That is we'll have the omega parameter next slide. When we have the two complex, minus sigma plus or complex omega minus sigma minus complex omega, we will have a by calculation get this value. It is first cosine and sine, cosine omega dt and sine omega. In exponential, we have the real part, that's real part. We have in exponential the real part. The complex part we have in sinusoidal part. Yeah. This is the complex part that we have in sinusoid part of the natural response. The next one is critically damped. What is critically damped? We have two real only at what? At pole sigma 1, real sigma 2 sigma 2 real at only sigma 1. The difference between critically damped overdamped, if you look at the equation, if you look at carefully, in overdamped we have two poles at 2 poles, so that's sigma 1 sigma 2, but in critically damped we have one pole. Actually, it fastest response without oscillating. It is the fastest response without what evaded oscillating. It is the difference between the underdamped and overdamped. Graphically shown. The undamped. What is undamped? In undamped, continuous. The system the response continues to oscillate infinitely. We have two imaginary, not too complex. Two imaginary. Our real part is 0 here. We don't have anything in real part. When our real part is 0, suppose this e to power t, yes, we have 0 multiplied by t, it is 0. E to 0 equal what? Equal 1. We have here 1. It means nothing affects. We didn't write. In real part we have 1. Real part we have 0, that our exponential part will become 1. The sinusoid part of the natural response will become like this, and by calculation using the mathematics, and this one, this one. One thing I forgot, sorry, about the critically damped. We have in second part, the exponential part is actually multiplied by a time also. Hope it is clear. Impact of pole location on response characteristics. That definitely the pole location impacts on the characteristics of the what responses. This example of the second order system, we have a representation, a short representation of a simpler representation of the general representation, and under the representation the graph is shown, and also the graph is shown here the way of the graph here. This is underdamped, this is also undamped, that is the graph, and undamped sinusoidal. This one is the last one, critically damped. This one, this one. This is a representation, graphically representation, and also modeling it simply taken from book. The next one. We have some parameters by the natural frequency, named on a natural frequency that is shown by omega. What is that? Actually, the system, it is a frequency that the system will isolate if there no damping. If there is no damping, the system isolates. The damping ratio, it means how a system isolates in a system, how isolations, for example, the system decay or decline or comes down after a disturbances. If we have this is a relationship, exponential decay frequency, natural frequency, radian per second, and that is the damping ratio is the ratio between the exponential frequency over the natural frequency. Using the poles, the position of poles as told in complex exponents help us to determine any type of the response without using more complex calculations actually. In conclusion, understanding the time response is critical for designing more efficient control systems, and also poles and zero provide essential very important information about the behavior of a system, and knowing the first and second order systems help us to in actually in practical application. I hope you got something from my presentation. Thank you. Nice to meet you. Assalamu alaikum.